Guys, this is the physics video, unit 3. We are in section 4, torque. We are introducing torque today in part 1, and we'll go into more detail about these things a little now and then also during rotational motion when we do a whole unit on that. So today's just a little intro. So I want you to think about this. So if you have a rod and you apply equal forces of equal magnitude to this rod, which would cause rotation of the axis? So I'm going to show different forces. I'm going to label them as red if they do not cause motion and blue if they do cause motion. You can either do this with colored pens on your paper, or you can X out the ones that do not cause motion as you're following along. So let's first look at a force that goes right into the axis. So if we are pivoting around a central point, if you apply a force right onto that central point, it will not cause any rotation. So that's why I'm doing it in red. Red for no rotation. What about if you go right on the edge and push into, again, straight into that axis? Nope, not going to cause anything. On the other side, still not going to cause any rotation. Okay, what about this force? So I've got a downward force on the left-hand side of my rod. And yes, that would cause rotation. Now notice all of these are the same size arrows. So these force vectors have the same magnitude, as in they have the same strength to them. They're just all being applied in different directions. All right, so how about this one? Will this make the rod spin? So if you push it at that angle hitting it, yeah, it's gonna spin. And what about at the very edge? Yep, that's gonna make it spin as well. So out of these forces, only the blue ones are going to cause rotation. And that is called having torque. So torque measures how rotation is produced as a result of a perpendicular force. So although this one is not perpendicular, it's only the perpendicular component. If you break up a vector and just say how much of that line is pointing perpendicular or making a 90-degree angle with what you're trying to push, that's what causes rotation. So here's your formula. So this is a lowercase tau Greek sign, and so torque equals equals radius times force. And what I mean by radius is if this rod started turning, what is the radius between the point of axis and where you're applying the force? So radius times force, since radius, and if you need to remember that, you want to write this down, that this is radius and that's force. The radius is length, so that's meters, and force is newtons. So torque is measured in newtons times meters, Newton meters, which sounds weird. You want to say per, it's not per, it's literally newtons times meters, so Newton meters. Okay. So out of the previously mentioned forces, which would create the most torque? So out of the three forces that I described on the last slide that do produce torque or rotation, so I've gotten rid of the red ones, the ones that don't produce any rotation, which of these is going to make it spin the most? So keep in mind these are all the same magnitude, so they all have the same oomph behind them. They are just applied at different points or in different directions. So out of these, the ones that produces the greatest torque, let's first look at its radius times force, and these are all the same, except for this guy, it's only the perpendicular portion, so it's just this little bit here. So also, the bigger the radius, the more the torque. So because of that, on the outer edge, a perpendicular force on an object, on the very edge, perpendicular to the object, that's going to create the most torque. All right, so let's do a practice problem. What is the torque on a bolt applied with a wrench that has a lever arm of 30 centimeters with a force of 10 newtons? Let's go over what all these things mean and how to draw your picture. And then I've said it before and I'll say it again. In physics, the very first thing you want to do with any problem is say, can I draw a picture? And if you can, get that artwork going. All right, so I've drawn part of this picture for you, the wrench, and I've got the bolt here in red. So let's draw the force. Got a 10 Newton force going on it. And when I draw things on my picture, I often leave out units just because I find for a lot of students, the extra letters does make it confusing. It doesn't make it wrong. It's just extra letters that if you're labeling things correctly, that this is a force, you don't really need it because you know forces for newtons. When it says a lever arm of 30 centimeters, keep in mind that torque is Newton meters, not centimeters. So you need to change that to meters. To go from centi to meters, or centimeters to meters, you have to divide by 100. So this is your lever arm, and it's basically just this straight line from the center to in line with your force. So if you want to draw a line that's parallel with your force that also goes across, then connect them, and that is your lever arm. Okay, let me say that again. See how this force keeps going, this line keeps going with the force? Okay, that's called your line of action. Basically, like the action of the force you're applying, keep in line with that action. It's very exciting. So here's the force that you're pushing that wrench with, and the line of action keeps going. Now you want to draw another line that is parallel to your line of action but goes through your axis. Your axis is on a bolt, and the straight line connecting them, that is your lever arm. Now, if you're doing something where it's like in the lab, how you had a meter stick and you put the weights on it, weights are automatically going to be perpendicular. You don't have to do this line of axis and lever arm. You just measure the radius. But if it's not a perfect angle, then this is what you need to do. Okay, so torque equals 0.3 times 10. So that's 3.0 Newton meters. That's how much rotation you're going to get. So with the same force, you would get more torque with a bigger wrench, because if you had a longer wrench, then your lever arm would be longer, which would make your radius longer, and with the same force, you could get more. So a bigger wrench makes easier work to do. All right, two things you need to know about torque. A clockwise rotation is considered negative torque, and a counterclockwise is positive torque. And that always makes people go, like, take pause, because, you know, why would counter be positive? But let me show you why. If you draw these pictures, so this shows a positive torque in the counterclockwise direction, and this shows a negative torque in the clockwise direction. And clockwise means it goes like a clock is going around. So generally, people are right-handed. So sorry to people who are left-handed. So if you look at each of these on the right-hand side, you can say, is it lifting up or lifting down? And if it's lifting up on the right-hand side of your circle, then it's a positive torque. So over here, you go to the right-hand side, it's not lifting up, it's going down. So that's why it's a negative torque, or just a little way to remember it. So when the sum of all torques is 0, meaning we add up all the total torques on a system, then it's at equilibrium, as in it's not going to rotate. So for example, if I have two equal masses on same distance from the center, so this is a 10 Newton mass, a 10 Newton mass, and they're both 0.2 meters from the center, then torque 1 is equal and opposite to torque 2. So let's show the math to see what I mean by that. The sum of all torques is equal to all the torques added up. So torque 1 plus torque 2. Now, if I had more torques, or if I had more masses on here, I'd say plus torque 3, plus 4, plus 5, plus 6, etc., however many you have. This just has 2 in my picture. So now we're going to use the formula to plug in to figure out our values. So torque 1 is the radius times force. And since this force is exactly perpendicular to our radius, I don't have to worry about the lever arm and all of that. I just can use this distance exactly, because this makes a nice 90-degree angle. Remember those right angles that go like that. All right, so sum of all force or torques is negative for torque 1 because it's pulling down on the right-hand side. So that's the negative sign. Radius is 0.2 and force is 10. So here is my torque 1. I'm adding that to torque 2, which is positive, so I don't add any signs. Radius is 0.2, force is 10, and when I plug this into my calculator, the sum of all torques is 0 Newton meters, which is why this system is said to be at equilibrium. It's balanced. So if all torques cancel, it happens when the magnitude of the positive torques, so however big the positive torques are, is equal to the magnitude of the negative torque. as in however big they are. So ignore positives and negatives. If they're the same total magnitude, then they cancel. So if you ignore this negative sign, you'll notice torque 1, which is in one direction, is equal to the magnitude of torque 2, which is in the other direction. So how about this scenario? So I have equal and opposite forces acting on this ruler or seesaw or whatever you want to call it. So initially I'm like, oh, I have equal and opposite forces. It's not going to move because my sum of all forces is 0. However, my torques don't cancel out. So torque 1 and torque 2, if you notice, are acting in the same direction. They're both going this way, so they actually add to each other. So the sum of all forces is still torque 1 plus torque 2. So now let's look. Are they positive or negative? They are negative torques. So the sum of all forces is negative 0.2 times 10 for torque 1 plus negative 0.2 times 10 for torque 2, which means my overall torque is negative 4 Newton meters. Since this is not 0, my system is going to start rotating. So even though the net force here was 0, there's still a rotation because those net forces aren't acting at the same point on my object. So if I'm balancing torques, like say here, notice I have two different forces or two different weights of objects. I have a 10 Newton mass and a 20 Newton mass. So to balance that out, since it's radius times force, the 20 Newton, which is twice as much as the 10 Newton, needs to be half as close to the center axis. So the magnitude of the left side torques equals the magnitude of the right torques. This is only talking about weights because the weights are both going down, so it's not talking about any up forces. So if I have radius 1 meter times 10 newtons on the left equals 0.5 times 20 on the right, they're both 10 Newton meters. The magnitude, so they are the same magnitude, opposite directions, so they end up canceling out and we don't rotate. So the net torque is 0, so there's no rotation. All right, that's it for the introduction to torque. Good luck, and I will see you in the next video.